welcome back, or welcome to the fifth talk of this series of talks on the vision revolution. I'm Dennis Connolly, this is Anne Cleary, we're the School of Looking, and yesterday, if you joined us yesterday, we were talking about visible light, unusually because most of these talks are about invisible forms of light. They've been about gamma rays and X-rays and UV light. And today we're going to go back to an invisible form of light, which is infrared, or IR.
That's right. We're going to talk about infrared, which is also a sort of a type of electromagnetic radiation. The difference between infrared and the other sorts is that, in fact, we sense it as heat. However, it is not heat. In fact, infrared has a heat signature, but it's not heat.
So in fact, all light has a heat signature, doesn't it?
Pretty
all light
much,
has a heat component, or
it does indeed. But this particular heat is within a range of wavelengths that we can sense or feel.
so it's like warm bodies. Would
exactly.
be,
You would be emanating infrared right now, as am I.
Okay.
So it was discovered in 1800 by William
a nice
Herschel.
round figure, 1800.
That's right.
So William Herschel was an astronomer.
That's right. He was an astronomer, but he was actually originally a musician, a German immigrant to Britain, and a self-taught astronomer. It wasn't until his 30s, he was in his 30s when he brought his first telescope and a book on astronomy, and really learnt it all himself. He became very, very interested in telescopes and was dissatisfied with the quality that he could find. So he then himself started to grind his own lenses to get an improved quality, and he became the first, the premier manufacturer of telescopes in Britain at the time.
Wow. So talented musician and talented lens grinder, and finally an astronomer,
an inventor,
and the man who discovered what he called heat rays.
That's right, heat rays. So he wanted to look at the sun. And he found that it was damaging to his eyes, and so he was experimenting with different types of glass and coloured glass to see what filtered out the sun best and made it, the most comfortable. And so he noticed that some of the glass was absorbing heat, was getting hot. In fact, what he said in his notes was, "When I used some of them, I felt a sensation of heat, though I had but little light, while others gave me much light, with scarce any sensation of heat."
Wow.
So he did a little experiment. He got a prism so that he could separate the light out into different wavelengths or different colours.
So a little bit like Newton, who we talked about. The very first talk was about Newton's experiment with two prisms.
That's right. Yeah. That's right. So this is really a corollary of Newton's experiment. He separated the light into wavelengths. He used cardboard, quite simply, to make sharp divisions between the wavelengths, and mercury thermometers with blackened glass bulbs to absorb the light. And
so there would have been a thermometer in each part of the spectrum, in fact, or he would have taken the temperature of each part of the spectrum.
That's right. He got a spectrum projected onto white paper or white board or whatever it was, and he placed the thermometers into these different areas of coloured light. So he could see that the heat temperature was mounting. Then he charted it, and he saw that it was continuing to go up. So he was.
It was continuing to go up beyond the red.
So then he did further experiments and placed a thermometer in the area beyond red, and found that it was going up again. And he continued. So he continued to chart it until he reached a peak, and then the temperature started to decrease again. And this actually is one of the original charts. I don't know if this is his original chart, but this is from an old publication showing.
So in fact, when this thermometer would have been receiving invisible light. So
right.
From his point of view, it was in darkness.
Exactly.
But nevertheless, it was heating up.
Exactly. Possibly not in full darkness. It was in normal daylight. or in a darkened room, and the spectrum was visible on the paper. So it wasn't full darkness, but it certainly wasn't in a ray of light, and yet it was continuing to heat up.
And we saw, when we looked at ultraviolet, we saw that a year afterwards, in fact, ultraviolet was discovered by using the same method on the other end of the spectrum.
That's right.
That was Ritter, and he had read of Herschel's experiment, and he decided that you could do the same on the other end. But he had some difficulty. He expected to find cold at the other end, since Herschel had found heat. But that's another story. But
I mean, Herschel could have quite simply put a thermometer at the other end, at the blue end, also in the dark, and seen that there was no change. But it wasn't getting colder.
Yeah. So essentially, the interesting thing when you look at Herschel, and this is a quotation from a letter that he sent to the king. I have looked further into space than ever a human being did before me. I have observed stars of which the light, it can be proved, must take 2 million years to reach the Earth. Wow. So he was talking about, even at that time, he understood that looking out into space was looking back in time.
Absolutely. I mean, they'd already discovered, they'd already made rudimentary attempts to measure the speed of light. A Danish astronomer, and what was his name again? Hang on a second, I have it here. Oh yes, Ole Romer had, over a century before, had managed to measure the speed of light, or attempt to, by observing eclipses of a moon of Jupiter. And he measured the time between the eclipse when Jupiter was closer to the Earth, according to his telescope, or further away. And he measured that and used that to deduce the speed of light with a relative amount of accuracy, not too badly.
So he knew what he was talking about when he said that the light was taking 2 million years to reach the Earth. And the interesting thing is, if Herschel could see what has become of astronomy today, he'd be very pleased, because his discovery of infrared was extremely important, and allowed astronomers to see much deeper into space than with visible light.
That's right. Because I mean, what we see with one of these very, very extraordinary telescopes, like the Hubble Deep Field Telescope, for example, is what we're seeing is.
Or before that was the Herschel.
The Herschel Space Observatory. We're seeing infrared, but we're seeing infrared from light from galaxies really very, very far away. And
the reason, now tomorrow we're going to be talking about microwaves, and we're going to explain this in much more detail, but galaxies that are very, very far away, the light has been travelling for billions of years, and during the time when it's travelling to us, space has been expanding, and while the space expands, the wavelength of the light expands,
stretches out. I mean, I would understand it also because those energy bands, or those wavelengths, must be losing energy over time. Because they've been sent out millions of years ago, and they're continuing to travel.
Cooling down.
So surely they cool down.
So in any case, they reach.
So we're getting IR, in fact.
What would have been visible light a few billion years ago is now infrared.
That's right. Right.
So the Hubble telescope, and before that the Herschel Space Observatory, and next year the James Webb Space Telescope, which will be launched next year.
Okay.
Extraordinary image of this. They all take imagery in infrared, and they see way beyond our galaxy images that are. I think this is probably the most beautiful and most thought-provoking image that has ever been taken of outer space.
So what are we seeing here?
So the Hubble telescope was able to take this extraordinary image, probably the most beautiful image ever taken, and the most thought-provoking image ever taken of the sky by any telescope. And Herschel would have loved to have seen this, because this is the Hubble's Ultra Deep Field Telescope, which is showing a tiny, tiny patch of sky. See this little box that's marked XDF?
Okay.
That's the patch of sky.
So that's what we're looking at.
And that's the scale of the moon.
Way past the moon, we're seeing all these galaxies, actually.
And a tiny, this whole picture represents 1 degree of the sky. 1 degree, 1 degree, if you take the whole sky, is 360 degrees.
So that tiny square, there's thousands of galaxies.
Within that 1 degree, there's one little square, and what you see inside it is there are 265,000 galaxies in that square that we
Wow.
can see.
My goodness.
And
And of course, they're all coming to us through infrared radiation.
and it's translating it then into visible light that we can see.
And of course, depending on the type of infrared, whether it's near visible or further away, they can tell how old the galaxy is. Some of these galaxies will not exist anymore because they've sent out their light millions of years ago.
Well, we don't know. We don't know if
They
they exist
may or may
really.
not.
I
We
mean,
just don't know.
the only information we have of them dates from billions of years ago.
Wow.
And some of these are very early galaxies. And the extraordinary thing about this image is it's like a Russian doll. You look in at one tiny part of the image and you see a galaxy, and you look at the tiny little dust around it, and you realise
Oh my goodness.
these are more galaxies. And probably if you looked
Wow.
closer into them, you would find more galaxies around them. It just goes on. It just gives you
Okay.
some idea of
Well, the mind is
hugeness,
blown by that.
hugeness of space.
So let's go, well, coming back down to Earth.
If we turn our eyes, our infrared sensitive eyes and our heat sensitive eyes back towards the Earth, and you don't really see back in time because the light is only recent coming to you, but we're looking at thermal
Indeed, this is a thermal image, so mapping areas of heat of from above the Earth, actually, a satellite image. And what we can see here, I think, is a storm gathering or swirling. And so we're seeing areas of heat, that red area in the middle and the green outside.
So that's essentially meteorology, the weather, but it's also the climate, isn't it? It also allows you to
Absolutely. Well,
to
infrared is
examine the
a
climate.
really important tool with regard to addressing climate change because it allows us to assess where heat islands are gathering, where polar caps are melting, where
Ocean
greenhouse
currents
gases-
are
exactly
changing.
greenhouse gases are accumulating, all of that from satellite imagery, and really very, very important tool. Actually, the greenhouse effect was first postulated by an Irishman. Did you know that?
No.
Okay, John Tyndall is his name. Actually,
Actually, the Tyndall National Institute that we're working with for the Crawford show, Invisible Light, that's named after him.
That's
I suppose.
right. Yeah. And so he,
Okay.
in 1859, he published a series of studies showing how greenhouse gases, including carbon dioxide, in particular carbon dioxide, trapped heat in the Earth's atmosphere. So,
Wow. So that's what we've got very used to this sort of imagery, the idea that we're not looking at colour, we're looking at temperature, and the temperature is translated into colour. When we go down onto the Earth, we can also look around us using machine eyes and see in the infrared. When you look at mountains and sky and buildings, you get an exotic image, but not one that gives you some enormous new information that's very useful to you.
well, it gives some information about the clouds, for example, different types of clouds.
Yeah, and you can see that the sky is warmer than the water. You can see that you can see where the sun is hitting the buildings is warmer.
That's right, and the little swan right there in front.
And you can see that. That's right.
We can
That's
see
right.
his
The
red.
swan in front is the hottest point in the picture, almost, isn't it? Yeah.
Okay.
So that's a warm-blooded creature in there.
Okay, but it's not telling us that much, actually.
No.
I
This
mean-
is not really what we have thermal imagery for looking at the landscape. Where thermal imagery becomes very useful is when we're looking at warm-blooded creatures.
Oh wow, this is so interesting. That little caterpillar on somebody's hand.
So a
Incredible.
caterpillar is cold-blooded, but
Yeah,
the hand is warm.
absolutely.
So you see, the caterpillar is almost not turning up. It's just
And
a neutral colour.
so looking at the lizard that's being held there as well. So what does it say if the lizard is purpley pink?
So the lizard appears to be is not as cold as the caterpillar,
But cold or a bit colder.
Yeah. And we see the range of temperatures that it covers, but the hand is way up there at the top, 95.
Okay, so getting up
I think
towards
that's
white and
Fahrenheit.
yellow are really hot. Okay, but this is a way of, I mean, this is a code, a colour coding really, but I mean, that's not how you would see
No.
if you actually had infrared vision, do you think?
Well, the interesting thing is what we do is we translate heat into colour when we look at and we're quite adept at doing it. We all understand what's warm and what's cold in these images. When we look at warm-blooded creatures like a dog or like any mammal or any bird. We understand that where the brightest yellow points are where we see the most heat.
That must come from looking at fires actually for millennia.
Yeah. And I guess the way we translate it is based on that natural common sense way. And our own bodies, of course,
this is so interesting. Look at all that red around about his neck and going up into his face.
Yeah, and you might understand that your body has a uniform temperature, but no, in fact, there's a...
And looking very closely at this, so going down through his arms is cooler because it's green going to blue. There's a hot patch around about his neck and going up to his head, and then cooler down towards the hands. But then the fingers, there's like a lot of pink in the fingers.
Fingers are warmer. No, are they? No.
Yeah, well, I think there's some more heat down there in the fingers.
No, I think the fingers are cooler.
Okay, so
in this particular system, the purple
like
is cool. Yeah.
Purpley pink is cool.
Yeah.
I see.
So it's possible to misunderstand.
His brain is cool too.
So this would be. Here you've got a range of ways of translating heat into colour. The basic thing would be just black and white, where the brightest points are warm and the darkest points are cool. And then you might add just a way of highlighting where the maximum temperature is in red.
Which is really interesting here in the dog, because we've got around his eyes, his paws, and also it's like his knee there, which is really strange.
I don't know where that would be. And then the most common way would be to render what's warm like molten metal, I guess, or like fire, and what is cold as blue, and then what's in between is purple. Okay, so that would probably be the most common way of looking at heat imagery, but it's become almost the convention. And then there's three other ways.
This is thermal imagery, but saying there are two different types of infrared visioning. Well, there are many different types, but one type is thermal information. Is actually taking the heat energy that we're emitting, or the infrared energy that is coming from a body, any type of heated or warm body.
Okay.
The other type is reflected infrared. Okay. And that is also has a lot of applications in night vision.
So when we see visible light, it's all reflected radiation from the sun or from a light source. And in infrared, we see reflected, but we also see radiated.
Exactly. Exactly.
So if you had an IR camera and an IR lamp, you could see the light that's being reflected from your IR lamp. Yeah.
Okay, so this is used quite often in bird watching, for example. You've got an IR, or in security as well. You've got an IR lamp that's projecting infrared, and of course, then you've got a camera that's just picking it up, but it's not heat that's emanating from the body.
Yeah,
it's simply reflected heat.
Yeah, exactly. Yeah, which is the same as what we see with visible light. So I think both those possibilities are there, but I think the real thing that's fascinating about IR is that it's a sort of superpower that allows you to see what's hot and allows you to see what's cold. And it's amazing how well we are adapted to understanding these machine eye images. If we had this as a natural sense, this would be a completely different sense from vision.
That would be incredible.
Which gives you
sort of
completely
superpower.
Different information and quite useful to us, really. I mean, on a very simple level, we can understand it very well. We're very, very good at translating heat into color. We understand that this is a hot cup of a hot beverage on the left, and that it's an ice cube on the right. We understand that it's a radiator on the left, and it's a ventilator on the right.
Absolutely. Yeah. And I mean, this is really interesting, because looking at this chair, you can see that somebody's just left the chair, or when this person's lifted a hand up, it's left a trace behind. So that would be an incredible superpower, because people could, you could tell people had been there as a detective. And
it would make it really is. It's more like smell than vision in this respect. More like a dog smell.
Like the trace of somebody.
A dog can follow a person's trace. And then we have extraordinary. These are very innocent images. We're going to come to less innocent images afterwards, but extraordinarily beautiful. The simple image of pouring cold milk into warm tea, and then the residue left behind. And pouring cold water over warm hands.
I love how this is the inky blueness of the water. It's quite extraordinary. Of course, it's deep cold. So it's represented by this dark blue.
And it becomes opaque, really.
And
And whatever's warm is bright, of course.
absolutely. Oh my goodness. Really. And this girl,
including whatever you warm up with
she's using a curling tongs. So her hair is getting really, really hot, and her nose is like light blue there.
It's cold.
So she's got a chilly nose.
And of course, this is extraordinarily useful, and it's been put to extraordinary amounts of use in insecurity, the ability to see at night time.
That's an interesting area, of course, because there's a whole question of surveillance. But if we could actually, see into people's homes, through their heat traces, then there'd be a lot of issues to do with privacy and invasive surveillance.
Exactly, and it's got extraordinary benevolent uses as well for firefighters who are blinded by smoke, but the heat information comes through smoke. And we've seen very recently how useful this is for looking at a crowd of people. And seeing who has a temperature and the uses.
But of course, this level of surveillance and it connects with facial recognition as well, and all sorts of ethical issues. So we're kind of, it's a fine line between how useful and this incredible new power would be, and then controlling abuses, I suppose.
And beyond that, so the real question is, what would it mean to be an animal? Who has this sixth sense? Who has this? What advantages would it give us?
Well, apparently, quite recently, some researchers have managed to insert a new cone or neuron, I think, into rats' brains to allow them to visualize infrared. So maybe soon we can. Maybe soon as human beings we'll be able to get heat vision and IR vision.
And this would be using rat's eyes to see heat.
People wouldn't have rat's eyes. The rat.
And it does exist in nature already. Snakes have a sense of have a heat sense.
The sensitive infrared camera picks up the faint heat of the snake as a vivid orange, and the warm balloon as a bright white.
Here he comes. Tongue flicking at it, moving his head with it. He definitely sees it. He definitely sees it. He's got eyes, but it is pitch black dark out here. So something else is telling him that balloon is there. It is absolutely dark. It cannot be using its eyes, but it's following the motion of that balloon. It knows that balloon is there.
I mean, would they actually see, like you've just seen, like those coloured images? Or
no, they wouldn't see an image. It would be more like something that would give them a sense of where there's a warm body and in what direction and how far away, perhaps.
Okay, so if we had that sense, then we would have been much better hunters, for example.
Possibly, yeah. And speaking of hunting, here we come to some imagery that you might find disturbing. This is the advantage it gives us: nighttime hunting. An unsuspecting animal, which has no idea that he can be seen.
That is so tragic.
You do feel sorry for it's a coyote, I think, and you feel even more disturbed by this imagery of a modern battlefield, soldiers. Quite difficult imagery to watch. But it gives you some idea of exactly what use this sixth sense has been put to.
The applications are really vast. And I suppose extremely useful in many ways, but also potentially so destructive when we.
And when you add it to more sophisticated technologies,
is it a heat missile?
Missile technology in general. It's been used for such a long time in missile technology to track
so maybe
not just the heat of human beings, but the heat of jets, the heat of.
So maybe it's fortunate that we don't have infrared vision, because we probably would have used it for much more destructive destructive.
We probably would have been even more deadly than we are.
Annihilated our species. Many,
our own species
many.
and every other one. Yeah. So that's some reflection on what it would mean to have IR vision. We're integrating an installation into our Invisible Light show in the Crawford that's devoted to infrared.
But
some
much
of these
more fun and light-hearted than...
Yeah, but some of these reflections are going to be in the piece.
So that's infrared, and that was our 5th talk in the Vision Revolution series for Clonmel Junction Festival. Tomorrow we'll be talking about...
microwaves.
Yeah.
So we're going back into space with microwaves,
right.
because we're going to be looking at the oldest light in the universe.
Wow. So I hope you can join us tomorrow for microwaves at the same time.
Thank you very much. Bye-bye.